Hello, so today we're going to look at the exam 3, the final exam for transport 2. In the first part of this, we're going to look at the Lewis relation. I guess we can write it down. And yeah, so that's the first part of this, and there'll be many, many parts. So the first part is to look at our dimensionless numbers. We have Sherwin, and then we'll put Nusselt's number up there also, and I'll describe it, and then we'll divide the two, and then we're gonna that'll be equal to the Lewis number. So what we're gonna do is it's actually equal to a. Let me get the. And Schmidt number to C. Okay, and then the same thing is going to work for Nusselt's number. It's just going to be Price number. So if we divide the two, Schmidt's number, Sherwin number by Nusselt's number, well, these cancel out. These terms cancel out. Schmidt's number, Price number, and that's equal to the whole thing to the C. I don't know if you can see that. The whole thing to the C, and that's going to be equal to Lewis's number to the C. So we could actually describe what that means. We know what Schmidt's number is, and we also know what Pritz's number is. So, and that'll all be to the. So we know that that Schmidt's number is equal to the I guess we just write like this. V, I guess that's the most efficient way to do it. It's going to be equal to V over diffusivity coefficient, and then the Price number is going to be equal to the same thing over viscosity, and that's to the C. And you can tell that, sorry, not over viscosity, it's over to the thermal coefficient. And then we're going to flip it. It's going to keep, change, flip, and these things cancel out. So you're left with thermal diffusivity over to the C. So that is equal to, I don't know if you can see that. There you go. So that is going to be equal to this. So we can look at what thermal diffusivity actually is. Just to create more space to go up. So, and then we can relate that more to the Lewis number, right? Because these two things are equal. So it's equal to K over CP, and then it should be density. So so basically we can put that into here and create a relationship between without just finding thermal diffusivity. So we have K over let's see. Okay, so now what we have found is a way to relate density and density without thermal diffusivity back to the Sherman and Nusselt's number. So now we can define those and find a way to relate those out. So I guess we got some space over here. So we can define these two terms. So Sherman's number is equal to KC over, D over DAB. And then Nusselt's number is equal to HD. You can see that, okay? HD over K. So now what we can do, since this is what we found before, is we can put those two over each other and make it equal to what we found over here. Sorry, my board's a little bit too close to our camera. So what we're left with is so it should be KCKD all over so it'll be DAB over HD. And that whole thing will be equal to K all over rho CPDAB, because that's what we found before. I forget rho. No, we're good. So now we can cancel out a couple of the terms, and we'll get KC. Let me see. So we cancel out KC over H, right? And then we'll get 1 over rho CP. Okay, and that's the Lewis relation, and that's how it describes back to these dimensionless numbers. So for the second part, we can talk about how this relates to the energy balance, and then we'll just keep on adding from there. All right, so now this is part 2. We already found the Lewis relation for the first part of this, and for the second part of this, what we're going to be talking about is wet versus dry bulbs and relative humidity. A little background for wet and dry bulbs. So basically the way that they work is they're temperature bulbs, and they're a way to measure relative humidity. So if you have a completely dry bulb, it's going to measure a certain temperature. And if you have something that's like, say, soaked in water, like completely soaked in water, then you'd find that the one that's soaked in water will actually read a smaller or a lower temperature, a colder temperature, than one without it. So that's a way to, like, if you put that into the atmosphere, it's a way to measure how much like water vapor is actually in the atmosphere. So yeah, so that's how wet and dry bulbs work, and you can measure relative humidity with that. So for this, we're going to be looking at the relationship of the energy balance between like the energy balance of this to determine the relationship between this, between this and wet and dry bulbs. Okay, so I hope that made sense. So we can go ahead and get started and look at the energy balance itself. So we can start with the mass coefficient, and that's going to basically we're looking at two sides of the balance, and basically on this side we're going to look at the difference in temperature, and on this side we're going to look at the difference in C. And it's gonna make a lot more sense once we do it. So now we can look at coefficient for the surface minus the atmosphere, because you're gonna have a difference in that's what's measuring. So hopefully a dry bulb, you have the same temperature all the way around. A wet bulb, when you have higher humidity, it's going to read differently. So you're gonna have a temperature or a difference. And then for this side, we're going to have C over H, and then we're going to have the temperature difference of the whole atmosphere. You can see that. Than the one on the surface. Did I do that right? Oh, sorry. Yeah, never mind. This is H. Sorry, I was getting ahead of myself. This is H. This is a pretty normal formula. Sorry, I've been doing this way too many times. So on this side, we actually need lambda. And the reason for that is because this is related to thermal. So we need something to represent that. Okay, so that should be good. So what we can do is now we can move that KC over here. Sorry, KC. That'll be lambda minus C. And obviously, see, this is why I was, this is different. Sorry. I must have wrote this down completely wrong. This is H over KC. That's why I was so confused. And it's good to know it off the top of your head just in case you make mistakes like I do. Okay, so that is the Lewis relation, and now we can put in rho Cp T Cs plus C infinity. Okay, that looks a lot better. So now we can relate this back to humidity and the temperature difference between the concentration of water, because it's going to be different, right? How much water is in the air. So basically what we can do is we can set the concentration. We know that it's P over RT. P over RT. Okay, so we know that it's P over RT, and we know that this is going to be water on the surface, and this is going to be air. So now, okay, sorry. Sorry. It'll be the water in the air. Yeah, that's better. So this is on the surface, and that is on this is on the surrounding area and the atmosphere. Okay, so on this side, what we'll end up getting is we'll relate it back to what we were doing before. So we'll have density over P, the temperature, and that will be over RT. Temperature. Make sure that you can see that okay. Okay, and then that's going to be equal to, we can just combine these terms so that they're both over RT. So that they're both over RT. And then sorry, this should be concentration, so 1 over, should be Cp. Okay, so what we're gonna do here is cancel out RT. So there. See that? Sorry, it's a little bit crooked. Cp pt T infinity minus Ts. And then with this formula, we find the relationship between relative humidity which is this relative humidity and the Lewis relation, by that relationship right there. Yep. This problem where I've written out the variables. This is what we found with A2. So now we're trying to find the relationship between adiabatic saturation temperatures and compare that to the wet bulb temperature. So so now we're going to okay, so we can start the problem by looking at what's going in. So we have the flow rate of air going in, and then we have the water flowing down here. And then, well, the water is down here. So then we have the pressure of water initially, and then we have the temperature going of the air going in, and then going out. We also have the mass flow rate, and we also have the temperature of it going out. And then we also have the pressure of the water funnel, which is going to be equal to the saturated pressure when it comes out. Okay, so we can start by comparing the enthalpies. So the enthalpy in is obviously going to be different than the enthalpy coming out. So we can start by it'll be air, and we should have a quite a large formula going in. So we have the enthalpy heat, the enthalpy of heat, and then we have the pressure of water initially, and then we also have that multiplied by the molecular weight. And then, sorry if I'm going a bit slow, I'm thinking about units. And then that'll all be over RT. So that should be, that would be equal to concentration of the water initially times the molecular weight. So then we're going to multiply that by RT, and that's going to cancel out our units. And then we're going to have PT times the molecular weight. This will be the molecular weight average. I guess I can write it as ABE. Hope you can see that. Okay, so molecular weight average. And then, actually, there's going to be another unit for this. And what that's going to be is it's going to be the sensible heat. So we're going to have Cp times T initial. And this whole thing is going to be multiplied by the mole, or the mass flow of air. So we get the same kind of thing for enthalpy out. So the whole thing will be multiplied by the mass flow of air, and then we'll also get lambda, which is enthalpy coefficient. We get the enthalpy coefficient, and then likewise it's going to be the same kind of thing, just finally. So we said that was saturated times molecular weight over RT. Okay, so it's all those things. It's pretty much the same kind of formula. You can see it, same kind of formula. It's just that it's going out, of course. So the next thing we're going to do is we're going to take the enthalpy out and then compare it to the enthalpy in. And to do that, basically we just set them equal to each other. So average plus CP. And then that whole thing is going to be equal to enthalpy out. So I'm just writing this out. Of course, a lot of these are going to end up canceling. I'm just rewriting what we have here and just setting them equal to each other. Okay, so hopefully you can fit that in the camera frame. Sorry, it's really cramped in here. So obviously these two are going to cancel out, and what we're going to be left with is we're going to have, here, what's the edge of it, equal to 0. So I'm going to move all of these over, and then I'm going to match the terms that are next to each other. So what we're going to do is we're going to have, and I'll just cancel these out while I'm doing it. Same thing with over here, that's not fine. And then I'll be left with similar terms. So we'll have, what do you see it? Okay, and alright. And then that's going to be subtracted by this. Look at P, saturation. Average. And then we're also going to get CPTI. So now we have two like terms that are together and they're both equal to 0. We can pull out as, so CP, obviously this whole thing's equal to 0. So obviously we can pull out as many like terms as possible. So this one's quite easy, it's CP. And then you got temperature, we can just T1 minus T2, that's probably better variables than what I had. So now we can pull out pretty much everything that is not related to the initial, the difference. So obviously the pressure here is going to be different than the pressure here, but the flow is going to be the same, the hue is going to be the same. The molecular weight is obviously going to be the same. So what we can do is we can pull out lambda, we can pull out MW, we can pull out MW average, and then we can pull out PT. So we pulled out this, we pulled out this, we pulled out this. So we should be left with PW minus P saturation. That whole thing plus that. So now we're left with an equation that we can compare to A2, which I guess I can put down here. Sorry, I was left with not so much space. PW of the surface, and then minus the atmospheric pressure. P minus the air. Okay, so obviously this thing is equal to each other, and I set this one equal to 0. It's not really a problem. So now what we can, actually this should be negative. So what we have is kind of the, we can compare the two. So now we see that this hasn't changed at all. All we're comparing is, instead of it being on the, and compared to the temperature bulb, the situation that I described before was it basically soaking, where whereas we're looking at the actual atmosphere, looking at this atmosphere being equal to what we're measuring. So since that happened, this is going to be equal to this. The only difference is that this was on the bulb, and this, the saturation is happening all the time here, instead of happening on only the surface of the bulb. So besides that, they're really, really similar, and yeah, we can move on. Okay, so this is the beginning of B. This is B1. We're looking at a cooling tower. We have, this is actually, designate this as DZ. So we have a cooling tower. We have gas flowing from here to here. We have water coming down from here to here. And they have flows, mg. Let me see that, okay. The flow of gas is mg. The flow of the flow of water, the liquid, is ml. The cross-sectional area, little a has units of m squared over m cubed, so big A has units of m. So when you multiply the two together, you should get the volume. So what we're looking for, three different differential equations. So we can start by looking for dy over dz. That's the mass fraction of this whole tower. So what we can start by doing is putting down the relationship between the concentration and the mole fraction. So what we'll do is we'll have Kc, and then we're going to have the difference of the concentrations. So we're going to have, we can call it C2 or C final. And then we're going to, going to have to find the area at which this is going through. So it should be little a multiplied by big A dz. That should get the length also. So, so that's not only this part, but it's also this part. So then on this side, we should have the difference of the mole fraction. So we're looking at the mole fraction of as it goes through the gas. So it should be gas, and then you should you also have to look at the difference in molecular. So you have the molecular weight, and then we also have it should be big A, and it should also be Y. Yeah, that looks good to me. So we can pull out from this constants. So we know that G is going to be a constant. We know that A is going to be a constant. We know that the molecular weight is going to be constant. So now we're left with dy. I can rewrite all of this. So now we're going to put all the terms and find dy dz. So we're left with canceling out A. I think that's it that we can cancel out. Kc, C1 minus C2. And then we should be left with little a all over the flow rate of gas. And then that's multiplied by molecular weight. So this is the formula for dy dz, and what we can do is we can also make this, we can reduce this more a little bit. we can put this in terms of pressure and temperature. So it's going to be RT, so we'll just put P1 minus P2. Wait, and then that's also going to be over RT, so we'll just put RT here. Gas. dy dz. Okay, so that's the most reduced form. Make sure that the camera can get it. So that's the most reduced form for dy dz. The next one that we'll be finding is the temperature differential in respect to z. All right, so now we can look at the differential of the temperature of water. And what we're gonna do first is we're going to go ahead and start with lay it out in the form of enthalpy. So the differential enthalpy of the liquid. And we can kind of, when we're doing this, we're layering it out so that we're able to include the differential, and then we'll be able to solve for it, algebraically pretty easily. So what we're going to do is we're going to multiply our mass flow rate by the concentration of that liquid. And then we're going to multiply that by the temperature differential as it goes down the cooling tower, and that should all be multiplied by A, and then sorry, I think it's a good cross. Okay, so the cross sectional of big A, and that's because it goes, cross sectional, so it goes that way. And then here, you can see it fine. We're going to set that equal to our key coefficient, and then that is going to be multiplied by the differential, well, not the differential, the difference in temperature from the gas to the liquid. And that whole thing is going to be multiplied by the area, and that's going to be multiplied by the volume. So now we're going to subtract, hope you can see that. Okay, so then that's going to be multiplied by another unit, or another kind of values over here, and that's going to be the heat added. So we have to pull that out, and it's going to be the enthalpy, and then we're going to have N, which is a diffusive flux, and that's going to be N of the water, and then we're also going to multiply that by, that's just, it would be one line of it, so we got to multiply that by AA and DZ. I hope you can see that all, okay? So now we're just going to solve for the differential of the temperature over dz. So we can go ahead and do that. What we're going to do is we're just going to divide we're just going to divide this, sorry, I was thinking for a bit, over dz, and then we're going to have to divide those things over. So we're going to get, I don't know why I put this either, is equal to HTG over T. And that whole thing is going to be divided by mass flow rate, the liquid, times the concentration, and then we're going to be left with A, dz went over there, A gets canceled, and we're going to subtract the heat coefficient times mole diffusivity of water. A gets canceled, and then that whole thing is going to be left with A, I believe. All right, so then this should be our formula for the differential for the temperature of the liquid, or water in this case. And then the next one that we're going to look at is the differential of the gas.